In 1977, humanity embarked on one of its most audacious ventures, launching the Voyager spacecraft into the vastness of space. These twin probes, symbols of our insatiable curiosity, ventured far beyond the familiar planets, aiming to uncover the mysteries of the very edges of our solar system. As we journey with the Voyagers, we bear witness to their incredible odyssey, exploring realms where no probe has ventured before. Their golden records, a testament to the human spirit, carry our greetings to any who might find them in the cosmic ocean. Yet our exploration does not end with the Voyagers. Far beyond the gas giants, in the shadowy fringes of our solar neighborhood, lies Pluto. This distant world, once a planet in our textbooks, now stands as a gateway to the outer solar system. Through the eyes of new horizons, we have glimpsed its wonders, towering ice mountains, vast nitrogen glaciers, and the enigmatic heart-shaped Tombau Regio. Pluto, in its silent beauty, challenges our understanding and invites us to delve deeper into the unknown. Beyond Pluto, whispers of an unseen world stir the scientific community. This elusive Planet 9, hidden in the darkness, bends the paths of distant objects with its gravitational embrace. Its existence, inferred from the strange orbits of trans-Neptunian objects, hints at a world yet to be seen, a planet at the very boundaries of our solar system. Join us on a journey to the mysteries on the boundaries of the solar system, where the Voyager saga, the enigmatic Pluto, and the elusive Planet 9 await. In the sweltering summer of 1977, a cosmic opportunity loomed on the horizon. The planets of our solar system were aligning in a way that happens only once every 176 years. This rare celestial event opened the way to the unknown and gave us a chance to embark on a grand journey to the outer planets. Using this happy coincidence, NASA engineers and scientists conceived of a mission in which two probes would slingshot from planet to planet, using the gravitational pull of each to propel them farther into the depths of space. The technological marvels that were Voyager 1 and Voyager 2 were equipped with the most advanced instruments of their time. From imaging systems capable of capturing Jupiter's swirling storms to magnetometers designed to study Saturn's magnetic fields, these spacecrafts were to rewrite our understanding of the solar system. But the journey to the launch pad was fraught with challenges, budgetary constraints, technological hurdles, and the boldness of the mission objectives pushed the team to the limit. Every component of the spacecraft had to be painstakingly tested, every system optimized for the rigors of space. As the launch dates approached, the excitement was palpable.
3, 2, 1. MDS, we have ignition, we have a liftoff.
Soaring into the skies, these twin messengers carried with them the hopes and dreams of all mankind, embarking on a journey that would forever change the way we think about the cosmos. When Voyager 1 and Voyager 2 traveled beyond the asteroid belt, they were greeted by the colossal presence of Jupiter, the gas giant that gravitationally dominates our solar system. These encounters set in motion a series of groundbreaking discoveries that would overturn our view of the outer planets. Armed with a host of sophisticated instruments, the probes peered into the planet's turbulent atmosphere, revealing the dynamic and violent nature of its storms. The imaging science system, a key component of Voyager's arsenal, captured stunning details of the Big Red Spot, a storm larger than Earth itself, and revealed never-before-seen features. But perhaps one of the most unexpected discoveries was the existence of Jupiter's thin ring system, a ghostly band of dust and particles girdling the planet. This discovery, made possible by the ship's photopolarimeter, disproved the notion the rings were a feature exclusive to Saturn. Among Jupiter's moons, Io stood out for its fiery temperament. The observations revealed a world with volcanic activity, the first time such phenomena have been observed outside of Earth. Moreover, Io is the most volcanically active body in our system, its surface forever changing under the inexorable forces of its interior. Images of towering plumes and lava flows have changed our understanding of geologic processes in the solar system. As the Voyagers continued their journey to Saturn, unprecedented beauty awaited them. The complex and intricate structure of Saturn's rings came into view, and the probe's cameras captured the subtle interplay of light and shadow among the countless ice particles. The scientific instruments aboard the spacecraft, especially the radio system, played a crucial role in studying the composition and dynamics of Saturn's rings. The data collected revealed the complex structure of the rings, including the mysterious gaps and braids phenomena whose formation continues to intrigue scientists to this day. Titan, Saturn's largest moon, was another highlight of the mission. Shrouded in a thick atmosphere, Titan was a world of mystery, its surface hidden from view. However, thanks to the ingenuity of Voyager's instruments, glimpses of this mysterious moon suggested the presence of liquid hydrocarbon lakes and a complex weather system, sparking curiosity and speculation about the possibility of life on it. The Voyager 1 and Voyager 2 encounters with Jupiter and Saturn have not only expanded our knowledge of the hot gas giants, but have also opened new frontiers in the exploration of the outer solar system. In the cold and distant reaches of our solar system, Voyager 2 set out for a solitary encounter with Uranus, the enigmatic ice giant. This historic encounter in January 1986 offered a glimpse of a world that had previously been just a pale blue dot in Earth-based telescopes. Uranus has presented an enigma to scientists with its peculiar tilted axis lying almost parallel to the plane of the solar system. This unusual orientation, with poles that alternately bask in the sun and languish in decades of darkness, has a profound effect on the planet's weather and atmospheric dynamics. As Voyager 2 approached, its instruments, including the narrow-angle imaging science system camera, began to capture unprecedented images of Uranus's atmosphere and its suite of moons and rings. The pale blue color of Uranus hid the complex structure of the atmosphere. Faint bands of clouds and previously invisible rings girdling the planet. One of the most striking discoveries was the nature of Uranus's magnetic field, revealed by the spacecraft's magnetometers. Unlike the Earth, whose magnetic axis coincides exactly with the axis of rotation, Uranus's magnetic field was found to be significantly displaced and tilted, suggesting a complex and possibly multi-layered internal structure. Leaving Uranus behind, Voyager 2 continued its journey to Neptune, the most distant of the known planets. In August 1989, mankind saw Neptune for the first time up close. A dynamic and turbulent world, at the center of which was the Great Dark Spot, a storm the size of the Earth. Neptune's atmosphere, buffeted by supersonic winds, paints a portrait of a planet alive with weather disasters. The spacecraft and its suite of instruments have delved into the mysteries of these winds, capturing the movement of cloud formations and the complex pattern of Neptune's faint rings. Among Neptune's moons, Triton stands out for its retrograde orbit and geologically young surface. Voyager 2 images of Triton showed a frozen landscape dotted with geysers spewing nitrogen gas and dust into space, hinting at a geologically active interior. Voyager 2's encounter with Uranus and Neptune have expanded the frontiers of our knowledge, revealing the diversity and dynamism of the outer planets. These fleeting visits have provided a treasure trove of data that continues to influence our understanding of the icy giants of the solar system. Moving farther and farther away with limited resources, mission controllers faced the difficult question of which instruments should be left operational. To extend the life of the mission, non-essential systems, including the camera, were planned to be shut down permanently. But in a moment that epitomized the human spirit of exploration and reflection, astronomer Carl Sagan proposed a bold idea. Before the camera goes silent forever, he suggested that Voyager 1 take one last picture of Earth, a farewell shot of our home planet from the edge of the solar system. On February 13, 1990, the spacecraft warmed up its cameras for 3 hours. The spacecraft's science platform then took a series of images from a distance of about 4 billion miles that would later be combined into a mosaic of the solar system. Among the myriad scientific achievements, it was Voyager 1's gaze toward its home planet that captured the collective imagination of humankind. That pale blue dot is a testament to our insignificance in the vast expanse of space and a poignant reminder of our shared responsibility to preserve and protect the only home we have ever known. In an odyssey that stretches beyond the bounds of human perception, Voyager 1 and Voyager 2 traveled beyond the confines of our solar system, traversing the vast, uncharted territories of interstellar space. This monumental passage marked the first time humanity had traveled beyond the heliopause, the boundary where the sun's influence wanes and the mysteries of the cosmos are fully revealed. The heliopause is the extreme boundary of the solar zone, or domain, where the solar wind, a stream of charged particles emanating from the sun, meets the interstellar medium, the matter that fills the space between the stars in our galaxy. At this boundary, the external pressure of the solar wind is balanced by the internal pressure of interstellar gas and magnetic fields, creating a turbulent region that marks the end of the sun's influence. When Voyager 1 approached this boundary in August 2012, it became the first man-made object to cross interstellar space, providing scientists with direct measurement of the boundary for the first time. At that point, the instruments aboard the spacecraft, though developed in the 1970s, continued to transmit invaluable data back to Earth, recording a sudden decrease in solar wind particles and a corresponding increase in high-energy cosmic rays from outside our solar system, increasingly revealing the history of our universe. Voyager's journey beyond our solar system has not only expanded our understanding of the universe, but it's also paved the way for future endeavors in the never-ending quest to explore space. Their legacy is captured in the vast amount of data about the outer planets, their moons, and the heliosphere, and continues to be a cornerstone for scientific research, influencing the study of fields ranging from planetology to astrophysics. These missions have provided insights into the dynamics of planetary atmospheres, the structure of rings, and the nature of magnetic fields, setting the stage for subsequent missions. In the spirit of Voyager's pioneering voyage, subsequent missions have been designed to delve deeper into the mysteries uncovered by the twin spacecraft. For example, the Cassini-Huygens mission expanded our knowledge of Saturn by deeply analyzing the planet's rings, moons, and atmosphere. Similarly, the Juno mission looked beneath Jupiter's clouds, revealing the secrets of its internal structure and magnetic field. Looking to the future, the scientific community is clamoring for dedicated missions to Uranus and Neptune. These proposed missions are aimed at a comprehensive study of the icy giants, exploring their unique atmospheres, complex ring systems, and diverse moons. Such studies will not only improve our understanding of these enigmatic planets, but will also shed light on the formation and evolution of the solar system. Among the myriad scientific instruments and revolutionary technologies aboard the Voyager spacecraft is a message not for us, but for the unknown, for the future, or perhaps for other space dwellers. That message is the golden record, a 12-inch gold-plated copper disc on which are recorded sounds, images, music, and greetings from Earth. The gold record serves as a time capsule, a snapshot of humanity and our planet at the end of the 20th century. Its contents have been carefully selected to show the diversity of life and culture on Earth, from the sounds of nature, such as birdsong and the sound of the ocean, to music from different cultures and eras, including Bach, Beethoven, and traditional music from around the world. Decisions about the content of the Golden Record were guided by the desire to present a comprehensive picture of Earth and humanity. The team, led by Carl Sagan, put a lot of thought into including content that would not only convey the complexity and beauty of life on Earth, but also reveal fundamental scientific concepts, such as the structure of DNA and the location of our planet in the solar system. The cover of the Golden Record is decorated with symbolic instructions, the universal language of science and mathematics, designed to tell potential aliens how to decipher the disk. These symbols explain the origins of the record and provide instructions on how to play the audio content, ensuring that the message is understood throughout the space, transcending language and cultural barriers. The record is a testament to humanity's hope and desire for contact, communication, and connection, not only with our future generations, but perhaps with other beings who will one day find this bottle tossed into the cosmic ocean, carrying a message of a small, distant world full of life and dreams. As Voyager 1 and Voyager 2 continue their silent odyssey into the depths of interstellar space, the task of keeping in touch with these distant explorers is becoming increasingly difficult. Billions of miles from Earth, the faint signals transmitted by the spacecraft take more than 22 hours to cross the cosmic expanse and come like whispers from the void. The Deep Space Network, an array of giant radio antennas scattered around the globe, serves as the ears of the Earth, listening intently to the faint signals of spacecraft. As the spacecraft travel farther into space, the ingenuity and foresight of the engineers who designed and built these probes becomes increasingly evident. The longevity and success of the missions can be attributed to an amazing feat of engineering. Designed to last only 5 years, the spacecraft have exceeded their expected lifespan many times over, thanks to redundant systems, robust construction, and the use of radioisotope thermoelectric generators, or RTGs, for power generation. These RTGs convert the heat generated by the decay of plutonium-238 into electricity that fuels the spacecraft's instruments and communication systems. As RTG power decreases, mission controllers are faced with making difficult decisions about which instruments should continue to operate. This careful management of dwindling resources ensures that the most important science instruments remain operational for as long as possible, continuing to collect invaluable data at the frontiers of space. Looking ahead, we expect the Voyagers to continue their silent journey long after their last instruments have fallen silent. Driven by the momentum of their initial launch and gravitational support, they'll drift as emissaries of Earth, perhaps for billions of years. The idea that these spacecraft may one day be the only remaining evidence of humanity's existence, taking the golden records into the cosmic ocean, has its poetic note. The final frontier for Voyager is marked not by a physical boundary, but by our ability to communicate across vast cosmic distances. But even as spacecraft fade into silence, their legacy lives on, a testament to human curiosity and the unquenchable desire to explore the unknown. In the shadowy depths of our solar system, far beyond the last known gas giant, lies a world shrouded in intrigue and mystery. This is Pluto. Once considered the 9th planet, it now occupies a separate category, at the center of heated debate and scientific curiosity. For decades, Pluto remained a blurry speck of light in our most powerful telescopes, a distant dot at the edge of our vision. It was a world waiting to be discovered, keeping its secrets in the cold, dark depths of space. At the dawn of the 21st century, an unprecedentedly ambitious mission began. The New Horizons spacecraft embarked on a billion-mile journey to explore Pluto's icy frontiers. What it discovered was astonishing in its diversity: towering ice mountains, huge nitrogen glaciers, and the legendary heart-shaped Tombaugh Regio, an object so large it can be seen from space. But these discoveries are just the beginning. Join us as we journey together into the icy depths of the outer solar system, where one dwarf planet is eagerly waiting to tell us its story. In the early 20th century, the search for a ninth planet, the mysterious Planet X, gripped the world of astronomy. The search was not just about adding another name to the list of planets. It was about understanding the unseen forces that shape the orbits of the then already known celestial bodies around us. At the center of this search was Lowell Observatory in Flagstaff, Arizona, where a young astronomer named Clyde Tombaugh embarked on a painstaking journey through space. Armed with a telescope and photographic plates, Tombaugh set out to scrutinize the night sky, inch by inch, in search of an elusive planet that eluded detection. On a February night in 1930, Tombaugh's diligence paid off. Among the countless stars, he spotted a moving object, a tiny speck of light that was unlike anything else he had observed. It was Pluto, a distant world named after the Roman god of the underworld, a discovery that would change the boundaries of our solar system. As the decades passed, Hubble's Space Telescope brought us closer to Pluto than ever before. Launched into orbit in 1990, Hubble's powerful lens pierced the veil of distance separating us from the outer solar system. The first images of Pluto were a revelation, transforming the distant dwarf planet from a mere glowing dot to a world with distinct features. These Hubble images provided the basis for a more detailed study. They showed Pluto's complex surface, marked by variations in brightness and color, hinting at a dynamic world waiting to be explored. An odyssey of discovery that began with a single blinking dot on a photographic plate has brought us to the threshold of a new frontier. Pluto, once a mere curiosity at the edge of our solar system, was about to reveal its secrets through a relentless pursuit of knowledge and a relentless spirit of exploration.
5, 4, 3, 2, 1. We have ignition and liftoff of NASA's New Horizons spacecraft on a decade-long voyage to visit the planet Pluto and then beyond.
In January 2006, humanity embarked on another of its most ambitious journeys. New Horizons, a spacecraft no bigger than a grand piano, was poised to cross the vast emptiness of space, heading for a world barely seen by human eyes. Its mission is to unlock the secrets of Pluto, a mysterious dwarf planet at the edge of our solar system. When New Horizons soared into the sky, it carried the aspirations of countless people who had devoted years to that moment. The journey was a marathon of cosmic proportions, spanning nearly a decade and more than 3 billion miles. With precision, it plotted a path through the void, guided by the gravitational slingshots of celestial bodies in its path. In 2015, after 9 long years, as New Horizons approached its distant destination, the whole world watched with bated breath. The first images were simply revolutionary. Pluto, which was once just a speck of light even in the most powerful telescopes, now appeared to be a world of mountains, valleys, and plains. The landscape that came into view was strikingly varied. Ice mountains, some as tall as the Rockies, rose proudly to the surface, their peaks shrouded in a blanket of methane snow. Sputnik Pallidie, a nitrogen ice plain, stretched across the entire dwarf planet, its surface mottled with a complex pattern of ridges and depressions. Among the most striking discoveries are signs of geological activity. Pluto, long thought to be a frozen relic from the dawn of the solar system, turned out to be alive. Glaciers of nitrogen ice slowly flowed across the landscape, and hints of cryovolcanoes indicated that this distant world was not as inactive as previously thought. New horizons leap into the unknown, bridge the gap between assumptions and reality. Pluto was no longer just a point of light in our telescopes. It was a dynamic world full of surprises and beauty waiting at the edge of our solar system. It was just the beginning of a new chapter in our understanding of the cosmos. Pluto's expanse of rugged landscapes is home to one of its most mesmerizing features, the Sputnik Planitia. This enormous heart-shaped glacier is not just a striking visual landmark. It's a geological marvel that's changed the way we think about this distant world. The origin of Sputnik Planitia is a story of cosmic forces. This vast basin, stretching more than 650 miles, is believed to have been formed by the impact of a massive celestial body, an event that changed Pluto's surface and possibly its entire geology. The basin was filled with various ices, mostly nitrogen, creating a smooth, reflective plain that contrasts sharply with the surrounding topography. The surface of Sputnik Planitia is modeled with a complex pattern of convection cells, each the size of a country on Earth. These cells are the surface manifestation of ice in slow motion, churning and flowing in response to the weak heat coming from Pluto's interior. This lava lamp-like process shows that Pluto is far from the inert, frozen world we once imagined. More mysteries lie beneath the icy facade of Sputnik Planitia. The uniform mass distribution in this region, obtained from spacecraft measurements, hints at the presence of a denser layer beneath the ice. Scientists speculate that this may be a subsurface ocean. It's possible that this reservoir could contain liquid water isolated by the ice crust above. Among other discoveries, scientists have also found that Pluto has an atmosphere hovering above its icy surface, as thin and fragile as an atmosphere can be on the cold fringes of the solar system. Composed mostly of nitrogen, with traces of methane and carbon monoxide, this thin veil provides clues to understanding the planet's most mysterious processes. The structure of the planet's atmosphere does not match the primary expectations. When New Horizons flew by, it found an atmosphere extending hundreds of miles above the surface, much more extensive than expected. This thin atmospheric layer is stratified and has a complex interplay of gases that scatter and refract sunlight, creating a mesmerizing blue hue that resembles Earth's own sky. Because Pluto's journey around the Sun is unlike any other planet in our solar system, with an orbital period of an unimaginable 248 Earth years, each season on Pluto can last decades. Its trajectory is markedly elliptical. It is much closer to the Sun at perihelion than at aphelion, and its axis is tilted at an angle of 120 degrees, resulting in extreme seasonal variations on its surface. As Pluto approaches its perihelion, the heat from the distant Sun, though faint, is enough to cause a remarkable transformation. Surface ices, composed of nitrogen, methane, and carbon monoxide, begin to sublimate, a process by which these ice change from a solid state to a gaseous state, without changing to an intermediate liquid state. This sublimation is most pronounced in regions exposed to the Sun's weak but constant rays, resulting in an increase in atmospheric pressure as gases previously trapped in ice form are released to the outside. This outgassing thickens Pluto's atmosphere, making it more substantial during these warm periods. The atmosphere expands, rising hundreds of kilometers above the surface, much more than during colder periods. This expansion is uneven, and it's influenced by Pluto's topography and the composition of its ice, creating a complex and dynamic atmospheric system. As Pluto continues its long journey, moving away from the Sun and toward more distant parts of its orbit, the atmosphere is undergoing a dramatic turn of events. The gases that once thickened the atmosphere are now cooling and condensing, falling back to the surface as a fine snow of nitrogen, methane, and carbon monoxide. This cyclical process of sublimation and condensation is a defining feature of Pluto's climate, changing its surface over the centuries. This dance of ice and vapor unfolding over the course of Pluto's long year paints a portrait of a world in constant motion. Far from a static, frozen wasteland, Pluto's surface is a dynamic environment, a reminder of the active and ever-changing nature of even the most distant members of our solar system. Another exciting discovery about Pluto's atmosphere is its escape rate. Unlike the strong magnetic fields and gravitational pull that protect the atmosphere of the larger planets, Pluto's weak gravity allows much of its atmosphere to escape into space. This atmospheric escape contributes to the ionized gas tail, an invisible comet-like trail that Pluto leaves behind it as it orbits the Sun. This leakage is not a steady, gentle flow, but a complex interaction with a solar wind, a stream of charged particles emanating from the Sun. These particles, colliding with escaping atmospheric gases, create a dynamic and ever-changing environment around Pluto, a miniature magnetosphere in which the drama of solar and planetary forces is played out. From Pluto's dynamic atmosphere and unique climate, we move to its largest moon, Charon, and discover relationships and landscapes that change the very definition of celestial bodies in the outer part of our solar system. Charon, Pluto's largest satellite, orbits in synchronized motion with it. Discovered in 1978, this celestial body turns out to be more than just a satellite. It is a whole world filled with geological wonders and a unique history that's intertwined with that of Pluto. As New Horizons flew past Charon, they saw a landscape of canyons so deep and wide they could easily swallow up parts of Earth's Grand Canyon. These chasms stretched across the surface of the satellite, telling a story of geologic upheaval. Mountains rising dramatically against the lunar surface reveal a dynamic history, their peaks casting long shadows over the valleys below. The origins of Charon's dramatic topography lie in its past, marked by internal processes and possibly cryovolcanic activity. As Charon cooled and compressed over millions of years, its crust split, resulting in vast canyons. At the same time, mountains may have formed from tectonic activity as the moon's surface flexed and broke, pushing some areas upward and raising peaks. The interaction between Pluto and Charon is a kind of gravitational ballet in which both bodies are locked in a synchronized orbit. This means that Charon always faces Pluto on the same side, and vice versa, a phenomenon known as tidal locking. Unlike most moons, which orbit around their planets, Pluto and Charon orbit around a point in the space between them, known as the barycenter. This unique arrangement challenges the conventional definitions of planets and moons, suggesting a binary system where both bodies are partners in their celestial tandem. This gravitational partnership extends beyond Pluto and Charon, affecting the orbits of Pluto's smaller moons, Styx, Nix, Kerberos, and Hydra. Charon's presence stabilizes these smaller satellites, maintaining the complex balance of the system. The dynamics of this mini-solar system give us valuable insight into the gravitational interactions that shape the orbits of celestial bodies throughout the universe. Located in the vast realm of the Kuiper belt, Pluto stands like a sentinel at the edge of our solar system. This region, a vast cluster of icy bodies extending beyond the orbit of Neptune, is a relic of the early solar system and holds the keys to understanding the formation and evolution of our cosmic neighbor. Pluto, once thought to be the ninth planet, has found its relatives among the vast number of Kuiper belt objects, or KBOS, like dwarf planets like Haumea and Makemake, to smaller, lesser-known bodies. Each KBO has its own story that contributes to the picture of the solar system. Pluto's varied landscape, from nitrogen ice plains to towering mountains and dynamic atmospheres, reflect the complexity and diversity of the Kuiper Belt landscape. The Kuiper Belt is a window to the past, a frozen archive of the birth of the solar system. The objects included in it, including Pluto, are remnants of the time of planetary formation, untouched by the sun's heat. Their composition, ice mixed with rocks, gives an idea of the materials that abounded in the early solar system and allows us to understand the processes that led to the birth of the planets. Exploring Pluto and its neighbors in the Kuiper Belt has far-reaching implications for our understanding of the solar system. Each mission, like the New Horizons flyby of Pluto and Arrokoth, peels away layers of mystery, revealing the conditions and processes that prevailed in the outer solar system billions of years ago, forcing us to consider the dynamics of planetary formation and the boundaries between planets and smaller celestial bodies. Pluto's position in the Kuiper Belt emphasizes the interconnectedness of celestial bodies, from the smallest piece of ice to the largest gas giant. The dynamics of the Kuiper Belt, with its resonances and orbital interactions, influence the stability and evolution of the outer solar system, shaping the trajectories of comets and affecting the environment of Neptune. However, New Horizons exploration didn't end there. After its historic flyby of Pluto, it traveled onward to Arrokoth, a Kuiper Belt object, meeting it on January 1, 2019. Marking the next milestone in space exploration. Arrokoth, resembling a clay snowman, demonstrated the soft merger of two primordial objects, offering unprecedented insight into the building blocks of the early solar system. The story of Arrokoth's formation is a testament to the slow and gentle processes that dominated the outer regions of the early solar system. The large lobe, called Bennu, is not a single formation, but a cluster of a dozen rocks, each more than 3 miles wide, huddled around a central slab. This cluster refutes previous notions of high-velocity collisions in planetary formation, suggesting instead a gradual merger at speeds of less than a dozen feet per second. This intricate interaction between two lobes, losing angular momentum and smoothly merging, forms an image of a patient cosmos where the building blocks of the planets come together in a heavenly cycle of gravity and time. Looking ahead, the horizon of solar system exploration is littered with potential. Concepts for the next New Horizons missions are already stirring the imagination of scientists and engineers. One of them envisions an orbiter capable of mapping Pluto's surface with unprecedented resolution, penetrating the mysteries of its small satellites, and even exploring the eternal darkness of the regions enveloped by Pluto's axial tilt. The project, inspired by the legacy of Cassini, proposes to use Charon's gravity to create complex orbital trajectories around Pluto, allowing for a comprehensive study of the dwarf planet and its satellites. Such missions could utilize electric propulsion, replicating the success of NASA's Dawn, and could potentially go beyond the Pluto system and explore new frontiers in the Kuiper Belt. New technologies such as direct fusion drives promise to propel future spacecraft to the outer solar system with unprecedented speed and efficiency. A report titled "The Fusion-Enabled Pluto Orbiter and Lander" from NASA's Innovative Advanced Concepts (NIAC) program describes a mission to Pluto with a direct fusion drive. Using a fusion reactor, a 1,000-kilogram orbiter and landing module could reach Pluto in just 4 years, more than twice the speed of New Horizons. These promising propulsion systems could significantly shorten the travel time, opening new pages in the exploration of the distant worlds of our outskirts. As we travel the vastness of space, exploring distant worlds and discovering the secrets they hold, our understanding of the cosmos continues to evolve. The story of Pluto, from its discovery to the present day, is a vivid reminder of the dynamic nature of science and our attempts to categorize the universe around us. Pluto's unique orbital interaction with Neptune adds another layer to its fascinating story. During its 248-year orbit around the Sun, Pluto appears closer to the Sun than Neptune for a brief time, challenging the view of its position as the 9th planet. This crossing of orbits, when Pluto and Neptune change places, occurs because of the elliptical trajectory of Pluto's orbit and its inclination relative to the plane of the solar system. Despite this temporal shift, Pluto's overall trajectory ensures that there's no risk of collision with Neptune due to their mutual orbital resonance. The rather lengthy debate over Pluto's planetary status has long sparked discussion and controversy that reaches far beyond the astronomical community. In 2006, the International Astronomical Union revised the definition of planet in our solar system, which led to Pluto's reclassification as a dwarf planet. This moment was not only a turning point for Pluto, but also a catalyst for the reclassification of celestial bodies. Pluto's history is closely tied to the Kuiper Belt, a region teeming with objects that blur the boundaries between planets, moons, and smaller celestial bodies. Studying Pluto and its neighbors makes us think about the wide range of characteristics that celestial bodies can possess, from their atmospheres and geology to their orbits and interactions. In the grand canvas of the cosmos, every thread, from the smallest asteroid to the mightiest gas giant, plays a critical role in the history of our solar system. As we stand at the threshold of new exploration, Pluto's legacy and the knowledge gained from the Kuiper Belt serve as beacons guiding us to a deeper understanding of our place in the universe. Rethinking our cosmic neighborhood is not just about the labels we place on it, but about embracing the diversity and complexity of the universe. In the vast, silent expanse of our solar system, beyond the familiar brilliance of Neptune, rumors of some unseen presence have been stirring astronomers for quite a few years now. This mysterious force, unseen but undeniable, stretches the very fabric of our cosmic neighborhood, bending the paths of distant objects with its invisible grip. Here in the shadowy depths of space, where the warmth of the sun barely reaches, lies a mystery that's baffled the brightest minds. The hypothetical world known only as Planet 9, whose existence can be determined not by direct observation, but only by the subtle interaction of trans-Neptunian objects performing complex orbital motion. Could there be a rogue planet, shrouded in the darkness of space, exerting its influence from afar? A world that defies our understanding and challenges the very limits of what we know about our solar system. Join us as we piece together clues scattered in the back of the solar system in search of a planet that has so far eluded our sight. In the early 1990s, the outer reaches of our solar system began to reveal their secrets. Astronomers discovered a region teeming with icy bodies, now known as the Kuiper Belt. This discovery marked the beginning of a new chapter in our cosmic journey, expanding our understanding of the boundaries of the solar system. Among these distant wanderers was Pluto, long considered the ninth planet and proudly bearing that title since its discovery in 1930. But as the Kuiper Belt uncovered its treasures, Pluto's status began to be questioned. The discovery of objects such as Eris, that rivaled and even surpassed Pluto in size, sparked a debate that shook the foundations of planetary classification. In 2006, the International Astronomical Union was faced with an unresolved situation. What defines a planet? The answer to this question led to a controversial decision that downgraded Pluto to a dwarf planet. This decision, met with both approval and opposition, has swept through the astronomical community and the public, redefining the way we think about the solar system. In this cosmic controversy, however, the seeds of a new mystery were sown: the peculiar orbits of some Kuiper Belt objects, including the then distant newly discovered Sedna, hinted at an invisible influence from the shadows guiding these icy bodies. Could it be that another planet, hidden in the vastness of space, created the architecture of the outer solar system? This question ignited the imagination of astronomers like Mike Brown and Konstantin Batygin, who set out to find the truth. Their journey will lead them to speculate on the existence of Planet 9, a hypothetical world hiding behind Neptune, whose presence is signaled only by the interaction of the most distant members of the Kuiper Belt. A new planet emerging from the heart of controversy awaits discovery. As we move beyond the familiar boundaries of the inner solar system, a realm of icy bodies and distant orbits opens up before us. Here, in the cold, dark regions beyond Neptune, lies an enigma that has captivated astronomers for years. It's the Kuiper belt, a vast ring of debris left over from the formation of the solar system. Among these celestial wanderers, a separate group shows peculiar behavior that contradicts the expected norms of orbital mechanics. These are detached TNOs, or trans-Neptunian objects, whose paths are free of Neptune's gravitational influence, and extreme trans-Neptunian objects, or ETNOs, whose orbits are so eccentric that they seem to be tethered to some invisible force. What could be the architect of this unusual behavior? The answer may lie in the gravitational anomalies that pervade this distant region. These anomalies, subtle but deep, indicate the presence of a massive object whose gravitational pull shapes the orbits of these distant objects. The detached TNOs, whose orbits seem to be unaffected by Neptune, hint at a disturbance in the gravitational harmony of the outer solar system. Meanwhile, ETNOs, with their extreme orbits, paint a picture of cosmic interaction guided by a hidden force. The quest to understand these gravitational mysteries led researchers to hypothesize the existence of Planet 9, a hypothetical world whose mass and orbit could explain these anomalies. By carefully mapping the orbits of these mysterious objects, scientists began piecing together the potential location and characteristics of this invisible planet. In the tranquil balance of our solar system, each planet plays its part, revolving around the sun in a centuries and centuries and centuries old rhythm. But beyond this familiar rhythm looms a shadowy figure, a silent participant whose presence is felt but not seen. Let's take a closer look at the Planet 9 hypothesis itself. In 2014, astronomers Chad Trujillo and Scott S. Shepard noted an intriguing similarity between the orbits of Sedna, 2012 VP-113, and several other ETNOs, a phenomenon too unusual to be a mere coincidence. Trujillo and Shepard made a bold suggestion: the existence of an unknown planet whose orbit is a perfect circle between 200 and 300 astronomical units from the Sun. A few years later, in 2016, Mike Brown and Konstantin Batygin embarked on an intellectual journey delving into the mysteries of the outer solar system in order to develop this hypothesis. Through careful analysis and computational modeling, Brown and Batygin pieced together previously found gravitational anomalies that indicated the existence of a massive invisible planet. This hypothetical world, in their opinion, could be the key to unraveling the special dynamics of the outer part of the solar system. As their research progressed, so did their understanding of the potential characteristics of Planet 9. Its mass was originally thought to be 10 times that of Earth, but further research revealed that its mass was slightly less, but still significant, at about 5 or 6 Earth masses. This revision painted a picture of a planet powerful enough to control the orbits of distant objects, yet elusive enough to remain hidden from our most powerful telescopes. The influence of this hypothetical planet extends far beyond its immediate vicinity. Its gravitational influence can explain the clustering of the orbits of detached TNOs and the extreme trajectories of ETNOs, weaving together a complex picture of celestial mechanics. The hypothesis of Planet 9 sparked a flurry of scientific research, and astronomers around the world joined the hunt for this elusive neighbor. The search for Planet 9 is a journey fraught with difficulty, a testament to both the vastness of the universe and the limitations of our current technological capabilities. Its distant orbit, presumably huge and elliptical, leads it through the farthest reaches of our system. This region, where the light of the sun is almost unattainable, envelops the planet in total darkness. This remoteness poses a serious problem because the potential position of the planet can encompass vast portions of the sky, requiring extensive, focused searches covering these celestial expanses in painstaking detail. It's something akin to trying to find a needle in an astronomical haystack. Moreover, because of its distance from the sun, the planet's surface temperature is extremely low, meaning it emits minimal thermal radiation, making infrared detection just as difficult. The lack of emitted and reflected light is compounded by the glare of distant stars and the myriad cosmic objects that fill the sky, each vying for the attention of our telescopes. Among other difficulties, the nature of the search is compounded by the planet's enormous orbital period, which is thought to be thousands of years. Because the planet's motion across the sky is imperceptibly slow from our earthly perspective. Even after a decade, Planet 9's position in space will have changed only slightly, making any attempt to observe its motion in the short term virtually impossible. This chilling rate of motion means that traditional methods of detecting planets by observing their transit or motion against the background of stars are not feasible. However, in their relentless pursuit, astronomers use an array of sophisticated techniques and instruments, from ground-based telescopes equipped with advanced adaptive optics to space-based observatories that circumvent the Earth's atmospheric distortions. So, in the pursuit of Planet 9, astronomers have had to go beyond traditional observational methods, leading to the development of several innovative approaches aimed at refining the elusive planet's location. They utilize unique aspects of the solar system's external environment and potential celestial interactions that Planet 9 may have with other objects. One of the proposed approaches has to do with potential moons that may orbit around Planet 9. Given its considerable mass, it is conceivable that it could have captured one or more moons during its long journey through the solar system. The concept is based on the process of tidal heating, a phenomenon in which the gravitational interaction between a planet and its moon causes internal heat to be released within the moon, potentially making it warmer than the parent planet. This is what allows the satellites Europa and Enceladus to have liquid subsurface oceans and also provokes vigorous volcanic activity on Io. This internal heating may cause the moons to emit infrared radiation more perceptibly than Planet 9 itself, providing an indirect but promising avenue for detection. Another innovative method involves tracking the trajectories of interstellar asteroids passing through our solar system. These high-speed objects, coming from regions outside our solar system, could potentially be affected by the gravitational pull of Planet 9. By meticulously tracking the trajectories of such asteroids, astronomers can infer the presence and location of a planet from the subtle gravitational jolts it exerts on passing bodies. This method was demonstrated by studying the interstellar asteroid Oumuamua, whose path through our solar system may have been slightly altered by such a massive object. The trajectories of spacecraft passing through the outer solar system can also provide valuable insights. Like asteroids, when spacecraft travel vast distances between planets, their trajectories are slightly and subtly influenced by the gravitational forces they encounter. By analyzing the precise tracking data from these missions, scientists can detect unaccounted gravitational anomalies that may hint at the presence of Planet 9. This method requires accumulating huge amounts of data over long periods because the gravitational effects are incredibly subtle. However, the results can be very significant and will pay off the time spent. Moving from direct observation to indirect detection through a planet's influence on its environment may be the key to unlocking one of the greatest mysteries of our cosmic neighborhood. The search for Planet 9 has also spawned many theories and speculations about the true nature of this elusive object. Among the most intriguing are hypotheses that Planet 9 could be a primordial black hole or a dense dark matter clump, each representing a radical departure from the traditional planetary view. The idea that Planet 9 could be a primordial black hole introduces a sharp twist to the narrative. Unlike stellar black holes, formed by the collapse of massive stars, primordial black holes are theorized to have originated in a high-density environment shortly after the Big Bang. These hypothetical entities may be the size of an asteroid, but have the mass of a planet. The possibility that Planet 9 is one of these ancient, mysterious objects is compelling for several reasons. First, it would allow us to explain the gravitational effects attributed to it without the need for a visible planetary body. Secondly, this of course does not completely contradict the impossibility of its detection, since such an object would theoretically be no larger than a basketball. According to another theory, Planet 9 may be a concentrated blob of dark matter. This form of matter, which does not emit, absorb, or reflect light, accounts for a significant portion of the total mass of the universe, but remains one of the greatest mysteries. Dark matter clumps, theoretical clusters of dark matter, are thought to have arisen from density fluctuations in the early universe. As the universe expanded and cooled, these gravitational fluctuations led to the formation of dark matter structures ranging from small clumps to massive halos surrounding galaxies. If Planet 9 were a dense cluster of dark matter, it could exert the gravitational influence observed in the outer solar system without being directly observable using conventional telescopic techniques. The primordial black hole and dark matter clot hypotheses emphasize the profound implications of the search for Planet 9 far beyond the discovery of a new member of the solar system. Whether it's an ordinary planet, a primordial black hole, or a dark matter clot, one way or another we'll find ourselves on the favorable side of events. The search for Planet 9 is a testament to humanity's enduring curiosity and relentless pursuit of the unknown. A recent preprint of a research paper by the same Mike Brown and Konstantin Batygin and their colleague Matthew J. Holman entitled Pan-STARRS 1 Search for Planet 9, dated February 1, 2024, reflects the meticulous ongoing efforts to uncover this enigmatic member of our solar system. The study used extensive data from the Pan-STARRS 1 survey, which, with its deep and wide sky coverage, provided a unique vantage point for the search. By focusing on single night transients and using a sophisticated Keplerian orbit linking algorithm, the researchers sifted through billions of detected objects, a task akin to finding a single grain of sand among the entire North American coastline. This methodological approach represents a significant leap forward, building on the foundation laid by previous surveys such as the Zwicky Transient Facility and the Dark Energy Survey. Despite the depth and breadth of the PS1 survey, the elusive ninth planet remained out of sight. No features matching the search parameters were found in the data. This result, while not leading to the discovery of a ninth planet, nevertheless narrowed the search area considerably, excluding 78% of the parameter space in which the planet could potentially reside. The remaining 22%, areas with poor observational coverage or inaccessible to current detection capabilities, represent the next frontier in this space search. The journey doesn't end with the PS1 research. The upcoming launch of the Vera C. Rubin Observatory promises to usher in a new era of astronomical observation with capabilities that can finally pierce the veil of mystery, including that which surrounds Planet 9. As we stand on the threshold of these future explorations, the search for Planet 9 remains a beacon of scientific inquiry, a reminder of the vastness of the universe and the small but significant place we occupy in it.